Traditional public transit operates in a state of blind routing. Fleets are dispatched, and administrators lose oversight the moment a vehicle leaves the depot. The core operational failure stems from disconnected data streams. Tracking vehicle locations, processing passenger tickets, scheduling maintenance, and calculating driver payroll all run through distinct, siloed systems. The standard industry solution is hardware-heavy. To monitor a fleet, operators typically deploy discrete, proprietary sensors, purchasing one device for GPS, another for fuel levels, and a separate camera for passenger security. Attempting to scale this across hundreds of vehicles multiplies the points of failure. Every new proprietary sensor requires distinct wiring, maintenance, and heavy upfront capital. Scaling modern fleet management has traditionally been bottlenecked by physical hardware costs and integration failures, not by software limitations. Shataj Soft Limited engineered an integrated transportation system to bypass this exact bottleneck. They deployed this architecture across major municipal infrastructures, including Jahangirnagar University and the Dhaka City Corporation. The core architectural pivot of their system is the complete abandonment of discrete proprietary hardware sensors. They implemented a mobile as an edge node strategy. Instead of installing industrial components, existing consumer smartphone technology is repurposed to gather and transmit industrial telemetry. This unified hardware approach channels all vehicle metrics, passenger counts, and personnel data into a singular centralized web admin panel. Fleet intelligence is achieved by collapsing hardware complexity at the physical edge to centralize operational complexity in the cloud. The foundational hardware unit of the Shataj Soft framework is simply a standard Android mobile device running a custom application. Look at this schematic of the device. The native GPS module is co-opted to stream live location data directly through Google Maps integration. A 4G GSM module maintains a continuous data uplink, pushing those metrics to the central server. The device's native NFC module is repurposed from processing consumer payments to count boarding passengers as they tap their transit cards. Simultaneously, the built-in mobile camera functions continuously as the onboard security feed. The system relies on exactly one external hardware dependency, a physical fuel sensor, wired to transmit real-time fluid data through the mobile's active uplink. A single, cost-effective commercial smartphone successfully replaces 5 highly specialized proprietary hardware installations. This telemetry network also manages the human personnel operating the vehicles, utilizing a dedicated bus validator hardware unit stationed at the entry door. A driver or helper logs their shift simply by tapping their ID card to the validator terminal upon entry. Instantly, the validator transmits this specific attendance data packet via the 4G network. The backend database receives the packet and logs precise entry and exit timestamps for the employee. These timestamps automatically trigger an overtime bill logic tree. The system calculates exact compensation based on the verified shift duration, requiring zero manual human input. This personnel data runs simultaneously with the continuous reporting of real-time fuel reserves, exact passenger counts, live locations, and video feeds. Personnel payroll transitions from a delayed administrative task into a real-time automated byproduct of simply boarding the vehicle. A massive stream of edge data is useless if it overwhelms the end user. The software layer must partition this raw telemetry. This diagram shows the data split. Raw ingestion occurs on the left. On the top right, the primary student app interface displays the live locations of up to 15 different buses simultaneously on the home screen. Clicking a specific vehicle node immediately reveals the designated route, the active driver's name, and their direct contact number. The architecture supports bidirectional communication. Students can send short text messages from their interface, which display directly on a monitor inside the vehicle for the driver. A secondary end-user tier accommodates the staff and teacher app. This partition grants capabilities strictly reserved for administration, primarily allowing staff to officially book vehicles and monitor those booking statuses in real time. Role-specific applications dynamically extract entirely different utilities, live tracking for students versus active booking for staff, from the exact same raw data stream. The integrated management layer organizing these operations is the 4 software web admin panel dashboard. Here, the system assigns digital job cards to every individual vehicle in the fleet. All historical repair data, specific parts replacements, and mechanical maintenance records are permanently archived within these vehicle profiles. Regulatory and bureaucratic compliance tracking runs parallel to mechanical maintenance. The software actively monitors the legal life cycles of vehicle registration papers and physical fitness certificates. Automated logic triggers notifications to administrators before any legal document lapses, removing the risk of compliance failures. The administrative dashboard forces reactive mechanical maintenance and manual paperwork into a proactive automated workflow. Zooming out, we see the complete operational hierarchy, extending from physical Android Edge nodes on the road up to the cloud software processing the telemetry. Governing a centralized database of this scale requires strict role-based access control. The standard admin tier operates with limited permissions. These users are restricted to viewing specific operational data and executing carefully defined input functions. This contrasts heavily with the upper tier of system architecture. The super admin tier holds absolute authority, retaining full read, edit, and deletion capabilities across every record in the entire system. Because raw, automated telemetry flows continuously from the physical edge, rigid, tiered data governance at the highest level is vital to secure the infrastructure. The Shataj Soft system achieves scale by successfully bypassing the trap of proprietary hardware fragmentation. Utilizing existing mobile architecture as a composite IoT edge node eliminates the physical capital barriers that typically stall fleet modernization. It creates systemic harmony, integrating mechanical vehicle tracking, like fluid levels and GPS, directly with human administration, such as payroll and passenger ticketing. This architecture demonstrates how disparate data points, from fuel levels to payroll, can be unified into a single functional stream. The future of scalable fleet management no longer relies on inventing and deploying more physical sensors. It relies on engineering smarter data synthesis from existing tools. True operational intelligence requires unifying the physical vehicle, the personnel, and the bureaucratic administration into a single automated digital system.